What if everything we know about life's origins is wrong? Tonight, we're going to explore an impossible discovery that's rewriting existence itself. You've probably heard about asteroids, rocky fragments drifting through space, but here's what most people don't realize. One asteroid, no bigger than 5 city blocks, has just revealed something that challenges every law of chemistry we understood. By the end of this journey, you're going to see our place in the cosmos in a completely different light. Before we dive in, if you find these cosmic explorations fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This story will change everything. Right now, as you sit reading this, there's something extraordinary happening in the darkness above your head. Look up at the night sky for a moment. Do you see those pinpoints of light scattered across the black canvas? Between those ancient stars, navigating silently through the cosmic void, travels an object that carries within its dark surface the deepest secrets of our universe's childhood. It's just a point of light against the stellar backdrop. You couldn't see it with your naked eye, even if you knew exactly where to look. But this small, seemingly insignificant rock holds 4.6 billion years of cosmic history locked within its ancient matrix, a time capsule from an era when our solar system was still forming, when Earth was nothing more than colliding fragments of dust and debris. This is BENNU. The name itself seems to whisper of eternity. Ancient Egyptian mythology spoke of BENNU, a divine bird associated with rebirth and creation, rising from primordial waters to begin new cycles of existence. The scientists who chose this name couldn't have known how prophetic it would prove to be. This celestial wanderer would indeed rewrite our understanding of creation itself, forcing us to reconsider everything we thought we knew about the origins of life. But let me help you visualize what we're dealing with here. BENNU measures approximately 490 meters across. Picture the Empire State Building lying on its side. That's BENNU. Now imagine that entire structure weighing 73 million tons. Denser than you might expect, but with the consistency of loosely packed charcoal. This is no solid, metallic asteroid. This is something far more interesting. Every 6 years, BENNU completes an orbital dance that brings it uncomfortably close to our planet. We're talking about a cosmic game of Russian roulette played out over centuries. Current calculations give us a 1 in 750 chance that this mountain-sized object will collide with Earth sometime before the year 2300. Those might sound like reassuring odds until you realize we're talking about an impact that would devastate entire continents. But here's what makes BENNU even more fascinating than its potential threat. As it tumbles through space, rotating once every 4.3 hours, this cosmic wanderer resembles a gigantic spinning top, a perpetual motion machine that has been turning for billions of years. Its shape isn't random. Gravitational forces and ancient collisions sculpted it into this distinctive form, like a potter's wheel spinning in the cosmic dark. The first thing that strikes you about BENNU is how incredibly dark it appears. Its surface reflects only 4% of the sunlight that strikes it. This makes it darker than charcoal, darker than the blackest volcanic rock you've ever seen. Why so dark? Because BENNU's surface is rich in carbon-based compounds that have been baking in the solar wind for billions of years, creating one of the darkest surfaces in our solar system. The temperature variations on this small world are absolutely brutal. When sunlight hits BENNU's surface, temperatures soar to 130 degrees Celsius, hot enough to sterilize medical equipment. But just meters away, in the permanent shadows, temperatures plunge to minus 73 degrees Celsius, colder than the surface of Mars. These extreme thermal contrasts create an environment that seems hostile to preserving delicate molecules. Yet somehow, This cosmic forge has become a vault for the most precious chemical secrets of our solar system's birth. For decades after its discovery in 1999, ground-based telescopes suggested BENNU had a relatively smooth surface. How wrong we were. When our robotic emissaries finally reached this distant world, they revealed a surface rougher than the most challenging mountain terrain on Earth. More than 200 boulders, larger than 10 meters, dot its landscape, with the largest measuring a staggering 58 meters across, the size of a city building perched on this cosmic mountain. But BENNU had another surprise waiting for us. This isn't a dead, passive rock drifting through space. BENNU is geologically active. Telescopes and visiting spacecraft have observed it sporadically, ejecting particles and rocks up to 10 centimeters in diameter into space. These mysterious outbursts happen without warning, suggesting internal processes we still don't understand. What could cause a small, cold asteroid to suddenly spit matter into the vacuum of space? Let me put BENNU's size into perspective another way. If you could somehow stand on its surface, which would be quite a feat given its almost non-existent gravity, you would weigh about as much as a paperclip. BENNU's gravitational pull is 100,000 times weaker than Earth's. A gentle push off its surface would send you floating into space, drifting away from this ancient world at walking speed. Here's something that makes BENNU even more enigmatic. It rotates backward. While most objects in our solar system spin in the same direction they orbit the Sun, BENNU rebels against this cosmic convention. Its axis is tilted 178 degrees from normal, meaning it essentially tumbles through space upside down and backward. This retrograde rotation hints at a violent past, perhaps a catastrophic collision that knocked it off its original spin. The asteroid's orbit itself tells a story of cosmic wandering. BENNU's elliptical path carries it as close as 0, 9 astronomical units from the Sun, closer than Earth, and as far out as 1.4 astronomical units, well into the asteroid belt region between Mars and Jupiter. This eccentric orbit means BENNU regularly crosses Earth's path like a cosmic pendulum, swinging through our neighborhood every few years. There's something else affecting BENNU's trajectory that most people never hear about: the Yarkovsky effect. As this dark asteroid absorbs sunlight and re-radiates heat unevenly due to its rotation, it creates a tiny but persistent thrust, like a cosmic thruster pushing it slowly but steadily toward Earth over thousands of years. This gentle push is gradually nudging BENNU closer to our planet, increasing the odds of an eventual collision. But perhaps the most intriguing aspect of BENNU lies in its classification. Astronomers categorize it as a Type B asteroid, meaning it's rich in carbon compounds and water-bearing minerals. Its surface contains veins of carbonates stretching up to 90 centimeters long, geological scars that tell of ancient water flowing through cracks in its parent body billions of years ago, when our solar system was young and chaotic. The story becomes even more fascinating when you realize that BENNU isn't just a fragment of one ancient world. Embedded within its carbon-rich matrix are pieces of Vesta, one of the largest asteroids in the main belt. This tells us that BENNU is a cosmic recycling project, a collection of fragments from multiple worlds that were shattered and reformed through countless collisions over billions of years. Every day, BENNU faces a constant bombardment from micrometeoroids, tiny fragments of cosmic debris that strike its unprotected surface at incredible speeds. Without an atmosphere to burn up these particles, each impact creates microscopic craters and splash patterns of melted rock. This process, called space weathering, has been sandblasting BENNU's surface for billions of years, constantly renovating its appearance while somehow preserving the ancient chemistry locked within. All of these characteristics, the dark, carbon-rich surface, the evidence of ancient water activity, The accessible orbit, the manageable size, made BENNU an irresistible target for detailed study. Here was a small world that promised to unlock secrets about the formation of our solar system and the origins of the organic compounds that would eventually give rise to life on Earth. Scientists realized they were looking at something unprecedented, a cosmic time capsule that had preserved samples of the primitive materials from which planets formed, materials that Earth had long since processed through billions of years of geological activity. If you wanted to understand what conditions were like when our solar system was born, BENNU offered a direct window into that ancient era. This small, dark asteroid represented an opportunity that comes along perhaps once in a generation, a chance to physically touch and analyze pristine samples of our cosmic origins. The stage was set for one of the most ambitious sample return missions ever attempted. A 7-year journey that would reach across millions of miles of space to collect just a few handfuls of this ancient material. But as we would soon discover, those few handfuls of cosmic dust would contain secrets so profound, so unexpected, that they would force us to completely rewrite our understanding of how complex chemistry and ultimately life itself emerges in the universe. The answer to unlocking these secrets would require something unprecedented, a robotic odyssey across millions of miles of empty space to physically touch this ancient world and bring pieces of it home. On September 8, 2016, at Cape Canaveral, a column of fire erupted beneath an Atlas V rocket carrying humanity's most ambitious asteroid mission, OSIRIS-REx, Origins, Spectral Interpretation, Resource Identification. Security Regolith Explorer rose from Earth's surface carrying instruments that represented entire laboratories compressed into spacecraft-sized packages. This wasn't just another space mission. This was humanity's attempt to reach back through 4.6 billion years of cosmic history and touch the raw materials from which our solar system formed. Think about what this mission demanded. Engineers had to design a spacecraft capable of navigating across 2 billion kilometers of space to rendezvous with a moving target just 490 meters across. Traveling at over 100,000 kilometers per hour, it's like trying to thread a needle while both you and the needle are speeding down separate highways on opposite sides of a continent. Except the highways are in space, and you have 7 years to get it exactly right. For 2 years, OSIRIS-REx sailed through the cosmic void, its trajectory precisely calculated to intercept BENNU's orbit at exactly the right moment. Mission controllers on Earth monitored every kilometer of the journey, making tiny adjustments to the spacecraft's path. Adjustments measured in centimeters per second that would prove crucial for success millions of kilometers later. The navigation challenge was extraordinary. Imagine trying to meet a friend at a specific street corner. Except your friend is walking and won't tell you which direction they're heading. The street corner is on the other side of the country, and you have to start walking 2 years before the meeting time. That's essentially what OSIRIS-REx accomplished, using gravitational physics and orbital mechanics to predict exactly where BENNU would be when the spacecraft arrived. In December 2018, after traveling through 2 billion kilometers of emptiness, OSIRIS-REx captured its first detailed images of its destination. What the spacecraft revealed shocked everyone involved in the mission. The smooth, relatively featureless surface that ground-based observations had suggested was completely wrong. Instead, BENNU appeared as a rugged, boulder-strewn world with a landscape more challenging than Earth's most difficult mountain terrain. But the mission had to adapt. Within weeks of arrival, OSIRIS-REx achieved something no human spacecraft had ever done before. It established a stable orbit around the smallest celestial body ever orbited by a human-made object. At just 680 meters altitude above Bennu's surface, the spacecraft was closer to its target than a commercial airliner flies above Earth. The gravitational field was so weak that OSIRIS-REx was essentially hovering, using tiny thruster pulses to maintain its position for nearly 2 years. The spacecraft became Bennu's artificial moon, methodically mapping every meter of the asteroid's surface with instruments capable of seeing details smaller than your fingernail. Laser altimeters measured the precise height of every boulder. Cameras captured images so detailed you could see individual pebbles. Spectrometers analyzed the chemical composition of rocks from orbit, revealing the carbon-rich, water-bearing minerals that made Bennu so scientifically valuable. The mapping phase revealed thousands of geological features that told the story of Bennu's violent past. Impact craters from ancient collisions, ridges where internal forces had cracked the surface, and those mysterious bright veins of carbonate minerals that spoke of water flowing through this small world billions of years ago. Every image sent back to Earth added another piece to the puzzle of Bennu's history and, by extension, the early history of our entire solar system. But OSIRIS-REx wasn't just there to take pictures. The spacecraft's ultimate goal required finding the perfect spot to collect samples. Mission scientists analyzed dozens of potential landing sites, looking for areas that were scientifically interesting, but also safe for the delicate sampling maneuver. They needed flat terrain free of large boulders, but also wanted access to the darkest, most carbon-rich material that would tell them the most about primitive solar system chemistry. As the mapping continued, Bennu revealed another surprise that transformed it from a passive chunk of rock into an active, dynamic world. The spacecraft observed sporadic jets of particles erupting from the surface, ejecting pebbles and dust into space without warning. These mysterious outbursts suggested that processes were still active inside Bennu, thermal cycling, perhaps, or the release of ancient volatile materials still trapped within its structure. After extensive analysis, mission scientists selected their target, a crater they named Nightingale, located in Bennu's northern hemisphere. This 8-meter-wide depression was relatively flat and safe for landing, but more importantly, it was filled with dark, fine-grained material rich in carbon compounds. Nightingale represented the best chance to collect samples of the primitive organic chemistry that made Bennu so valuable for understanding life's origins. The sampling attempt would be OSIRIS-REx's moment of truth, and the mission team knew they would have only one chance to get it right. The spacecraft couldn't land on Bennu in the traditional sense. The asteroid's gravity was far too weak to hold it down. Instead, OSIRIS-REx would have to perform a carefully choreographed touch-and-go maneuver, descending slowly to kiss the surface for just a few seconds before retreating to safety. To prepare for this critical moment, the spacecraft performed 2 complete dress rehearsals, descending to within 40 meters of Bennu's surface to test all systems and refine the precise timing needed for sample collection. These practice runs revealed just how challenging the actual sampling would be. At such close range, every boulder and ridge on Bennu's surface became a potential hazard that could damage the spacecraft. October 20th, 2020, marked one of the most ambitious robotic achievements in space exploration history. OSIRIS-REx began its final descent toward Nightingale Crater, guided by autonomous navigation systems that had to react faster than radio signals could travel between Bennu and Earth. For the critical final moments, the spacecraft was entirely on its own. The descent took over 4 hours, with OSIRIS-REx slowly spiraling down toward the surface like a cautious insect approaching a flower. At just 125 meters altitude, the spacecraft's hazard navigation system took control, using LiDAR and cameras to guide the final approach with centimeter precision. The margin for error was virtually zero. A mistake of just a few meters could send the spacecraft crashing into a boulder or missing the sample site entirely. Contact. For exactly 6 seconds. OSIRIS-REx's robotic arm touched the surface of BENNU, while the touch-and-go sample acquisition mechanism fired a burst of pressurized nitrogen gas. The nitrogen blast disturbed the surface materials, creating a cloud of particles and pebbles that were immediately sucked into the spacecraft's collection chamber. In those brief moments, humanity reached across the solar system to gather pieces of its own cosmic origins. The sampling mechanism worked beyond all expectations. Instead of the minimum 60 grams of material that mission planners had hoped for, OSIRIS-REx collected approximately 122 grams of BENNU's ancient surface, enough material for multiple generations of scientists to study and analyze. The sample chamber was immediately sealed, protecting these precious fragments from any possibility of contamination and preserving them in the pristine conditions of deep space. In May 2021, OSIRIS-REx fired its engines one final time in the vicinity of BENNU, beginning the long journey home. As the spacecraft slowly drifted away from the asteroid, cameras captured final images of the world that had been its home for nearly 3 years. BENNU continued its ancient orbit, but it was no longer quite the same. Humanity had touched it, sampled it, and claimed a small piece of its 4.6 billion year story. The return journey required the same precision that had characterized the entire mission over 2.5 years. Mission controllers made tiny course corrections to ensure that the sample capsule would arrive at exactly the right point in Earth's atmosphere, at exactly the right angle, at exactly the right speed. A few meters error in targeting could mean the difference between a successful sample return and losing these irreplaceable specimens forever. On September 24, 2023, the moment of truth arrived. The sample return capsule separated from its mothership and plunged into Earth's atmosphere at 12.7 kilometers per second, protected by a heat shield as it carved a brilliant streak across the Utah sky. Parachutes deployed perfectly, bringing humanity's cosmic treasure down to a gentle landing in the Utah test and training range, where recovery teams had been waiting with all the precision of a military operation. The capsule was immediately secured and transported in a controlled environment to NASA's Johnson Space Center in Houston, where it would be opened in clean rooms that rivaled operating theaters in their sterility. When scientists first cracked open the sample container, they were greeted by the sight of material darker than charcoal and an unexpected discovery, a faint but distinct aroma, slightly musky and metallic, rising from rocks that had been sealed away from Earth's atmosphere for billions of years. Within weeks, small portions of BENNU began their distribution to laboratories around the world. Scientists in the United States, Europe, Asia, and dozens of other countries received their allocated samples, beginning a global research program that would reveal secrets locked away since the formation of the solar system. Each grain of this ancient material represented a messenger from an era when Earth was nothing more than cosmic debris, carrying information about the chemical processes that would eventually give rise to life itself. The stage was now set for discoveries that would exceed everyone's wildest expectations, revelations about the nature of organic chemistry in space that would fundamentally change our understanding of how life emerges in the universe. As scientists began their first tentative analyses of these cosmic specimens, they realized they were holding something unprecedented in their hands, material older than the rocky planets themselves. When Dr. Daniel Glavin and his team at NASA's Goddard Space Flight Center placed the first grains of BENNU under their most powerful analytical instruments, they knew they were looking at something extraordinary. But nothing had prepared them for what those initial measurements revealed. These tiny fragments of cosmic dust preserved chemical compositions that predated the formation of Earth, Mars, and Venus. They were holding pieces of the original chemical recipe from which our solar system's rocky worlds were built. Think about that for a moment. The rocks beneath your feet, the mountains, the ocean floors, all of it formed through billions of years of geological processing that mixed, heated, and transformed the original materials beyond recognition. But BENNU had somehow preserved samples of the primitive chemistry from before any of that processing began. It was like finding an unopened time capsule from the very dawn of planetary formation. The carbon content alone was staggering. BENNU contained approximately 4.7% carbon by mass, a concentration 5 times higher than typical carbonaceous meteorites. This wasn't just unusual, it was unprecedented. Most cosmic material contains trace amounts of carbon, but BENNU was practically saturated with it. The implications were immediately clear. This small asteroid had somehow preserved organic matter on a scale that defied conventional understanding of space chemistry. But here's what made the discovery even more remarkable. When you think of preservation over billions of years, you imagine conditions like the frozen depths of Antarctica or the dry chambers of Egyptian tombs. BENNU had preserved these carbon compounds in the harsh environment of space, bombarded by radiation, subjected to temperature swings of hundreds of degrees, and constantly pelted by micrometeoroids. Yet somehow, the organic chemistry remained intact. The water story was equally astounding. Approximately 80% of BENNU's sample consisted of hydrated minerals, rocks that had chemically bonded with water molecules billions of years ago and held onto them ever since. This wasn't just moisture trapped in tiny pores. This was water that had been incorporated into the crystal structure of minerals when our solar system was still in its infancy, just millions of years old. Electron microscopy revealed textures that told the story of BENNU's violent past. The material exhibited what geologists call brecciated structures, angular fragments of rock welded together by impact processes. These weren't simple cracks or breaks. These were the signatures of catastrophic collisions that had shattered BENNU's parent body into fragments. Then gravity and further impacts had reassembled some of those fragments into the asteroid we know today. But here's where the story becomes truly extraordinary. Despite this history of violent destruction and reassembly, despite billions of years in the cosmic shooting gallery of space, the delicate chemical signatures had survived. Mineralogical thermometers revealed that when water flowed through BENNU's parent body in the distant past, temperatures were remarkably benign, around 25 degrees Celsius. These were conditions more like a warm spring day on Earth than the extreme environments you might expect in the primitive solar system. The discovery of water-soluble phosphate minerals added another layer to the mystery. Phosphates are crucial for life as we know it. They form the backbone of DNA and RNA, and they're essential components of cellular energy systems. Finding them in soluble form suggested that BENNU's parent body had once hosted flowing liquid water, perhaps even a subsurface ocean. We might be looking at fragments of a small, vanished water world that existed in the early solar system and was destroyed billions of years ago. Analysis of microscopic grains within the samples revealed something that sent shockwaves through the scientific community. BENNU contained 6 times more pre-solar material, dust grains, that formed around other stars before our sun even existed, than any other extraterrestrial sample ever studied. These tiny particles, each smaller than a bacterium, were relics from stars that lived and died before our solar system was born, somehow surviving the turbulent formation of planets to be preserved in this cosmic archive. The presence of specific minerals told an even more detailed story of BENNU's aqueous past. Serpentines, magnetites and carbonates, all minerals that can only form in the presence of liquid water, were abundant throughout the samples. This wasn't evidence of brief, isolated water activity. This was proof of extensive, long-term circulation of aqueous fluids through BENNU's parent body for hundreds of millions of years. Isotopic analysis provided a cosmic GPS system, revealing exactly where in the early solar system BENNU's materials formed. The specific ratios of different isotopes pointed to the outer regions of the protoplanetary disk, where water ice was abundant 4.6 billion years ago. BENNU's ingredients had formed in the cold, distant reaches of our forming solar system before being transported inward to their current orbit. Crystallographic studies revealed structures frozen in time. Crystals of olivine and pyroxene retained their original orientations from the solar nebula. Like microscopic photographs of the conditions during planetary formation, these weren't rocks that had been melted and recrystallized. They were pristine samples of the original building blocks from which planets condensed. Perhaps most intriguingly, BENNU's overall density of just 1.19 grams per cubic centimeter made it less dense than liquid water. This meant the asteroid was essentially a cosmic sponge with a highly porous internal structure. Rather than a solid rock, BENNU was more like a loosely bound collection of fragments held together by weak gravitational attraction, a rubble pile that could be easily disrupted but somehow held its precious cargo of ancient chemistry intact. When the sample containers were first opened, researchers noticed something unexpected, a subtle but distinct aroma rising from the material. The scent was described as slightly musky with metallic undertones, reminiscent of wet earth and oxidized metal. This wasn't contamination, it was the smell of organic compounds that had been sealed away from Earth's atmosphere for billions of years, finally reaching human senses across the vast gulf of space and time. Compositional mapping revealed that BENNU wasn't uniform. Different regions of the samples showed distinct chemical signatures. This heterogeneity suggested that BENNU was a mosaic, assembled from fragments of multiple parent bodies with different geological histories. It was like holding pieces of several different ancient worlds that had been destroyed and remixed by cosmic collisions. Magnetic measurements detected an extremely weak residual magnetic field trapped within some minerals. This faint magnetic signature was evidence that BENNU's parent body had experienced enough internal heating to undergo partial differentiation, the process by which denser materials sink toward the center while lighter materials float upward. Even this small world had once been geologically active. Chemical analysis revealed anomalous concentrations of platinum group metals, platinum, palladium, and related elements that are extremely rare on Earth's surface. These concentrations were far higher than expected, suggesting direct contributions from nearby supernova explosions that had enriched the region of space where BENNU formed. We were literally holding stardust from stellar explosions that preceded our sun's birth. High-resolution imaging revealed impact features on individual grains, nanometer-scale craters, and splash patterns of impact glass that recorded billions of years of bombardment by cosmic dust. Each tiny particle carried a history of constant pelting by micrometeoroids, creating a record of the space environment that stretched back to the formation of the solar system. Noble gas analysis provided precise chronometers for BENNU's history. Trapped argon and other inert gases confirmed that individual components of the sample were indeed older than 4.5 billion years, making them among the most ancient materials ever studied in terrestrial laboratories. Mineralogical zonation patterns revealed multiple episodes of water-rock interaction, like tree rings recording seasons of growth. Chemical variations in mineral grains documented distinct eras when water flowed through different parts of BENNU's parent body under varying conditions of temperature and chemistry. The presence of complex sulfide minerals indicated reducing chemical environments with active hydrothermal systems, pyrite, pyrrhotite, and other sulfur-bearing minerals pointed to conditions that would have been highly favorable for complex organic chemistry, the kind of environment where simple molecules might spontaneously organize into more complex arrangements. Thermochemical analysis painted a picture of remarkably gentle conditions during BENNU's most active period of aqueous alteration. Temperatures between 15 and 80 degrees Celsius, the perfect range for preserving delicate organic molecules while still allowing chemical reactions to proceed. These were conditions that seemed almost designed for nurturing complex chemistry. As these initial findings accumulated, scientists began to realize they were looking at something far more significant than just another asteroid sample. BENNU was revealing itself as a chemical time capsule that had preserved not just the ingredients of planetary formation, but evidence of processes that might bridge the gap between simple cosmic chemistry and the complex molecular systems that eventually gave rise to life. The real revelations, however, were still to come. In November 2024, in the sterile laboratories of NASA's Johnson Space Center, something happened that made every scientist in the room stop what they were doing and stare in disbelief at their instruments. Dr. Yoshihiro Furukawa was hunched over an electron microscope, examining what appeared to be just another fragment of BENNU's dark matrix, when his spectrometer began registering signals that shouldn't exist. The molecular signatures appearing on his screen were so unexpected, so fundamentally impossible according to everything we knew about chemistry in space, that his first instinct was to assume equipment malfunction. But the readings were consistent, run after run, sample after sample. The instruments kept detecting the same impossible molecules, complex sugars, preserved in pristine condition after billions of years in the hostile environment of space. Let me help you understand what this means. Sugars are among the most fragile molecules in organic chemistry. They break down rapidly when exposed to heat, radiation, or even mild chemical stress. Finding them intact after billions of years in space would be like finding a delicate flower preserved perfectly in the heart of a volcanic eruption. It simply shouldn't be possible. The first confirmed detection was ribose, a 5-carbon sugar that forms the backbone of RNA molecules. This wasn't just any organic compound. This was one of the fundamental building blocks of genetic information, the sugar that allows RNA to store and transmit the instructions for life. For the first time in scientific history, we had definitive proof that this crucial molecule existed in pristine extraterrestrial material. But ribose was just the beginning. Furukawa's team soon confirmed the presence of glucose, the 6-carbon sugar that serves as the primary energy currency for virtually all life on Earth. Think about that. The sugar your cells are using right now to fuel your brain as you read these words. The same molecular structure that powers everything from bacteria to blue whales existed in space before Earth even formed. The implications hit the scientific community like a thunderbolt. With the previous discoveries of nucleobases and phosphates in BENNU samples, and now the confirmation of ribose, we suddenly had all the essential components needed to build RNA molecules. BENNU had become the first extraterrestrial object confirmed to contain every single ingredient necessary for constructing the information-carrying molecules that many scientists believe preceded and gave rise to DNA-based life. What made this discovery even more remarkable was what wasn't found. Despite extensive searching, no traces of deoxyribose, the sugar component of DNA, were detected anywhere in the samples. This absence was as significant as the presence of ribose, because it strongly supported the RNA world hypothesis, the idea that life originally evolved using RNA as its primary information storage molecule before later developing the more complex DNA system we see today. The preservation of these sugar molecules challenged everything scientists thought they knew about chemical stability in space. Under normal circumstances, sugars should decompose within thousands or millions of years when exposed to cosmic radiation and temperature extremes. Yet here they were, intact after 4.6 billion years. Something had protected them, preserved them against all odds in a cosmic deep freeze that defied scientific explanation. The concentrations were significant enough to rule out contamination or measurement error. These weren't trace amounts that might be dismissed as laboratory artifacts. Ribose and glucose appeared in measurable quantities that suggested efficient synthesis processes had operated in the primitive solar system environment. Whatever had created these molecules hadn't done so accidentally or sporadically. It had been a robust, systematic process. The analytical techniques required to make these discoveries pushed the boundaries of what was scientifically possible. Mass spectrometers sensitive enough to detect picograms of material, quantities so small that billions of molecules would be invisible to the naked eye, revealed organic chemistry with a precision that had never been achieved in extraterrestrial sample analysis. Every molecule had to be accounted for, every potential contamination source eliminated. Chemical analysis revealed the likely synthesis pathway for these remarkable molecules. Evidence pointed to formaldehyde reactions in aqueous environments with neutral to slightly alkaline pH, surprisingly gentle conditions for such complex chemistry. This wasn't synthesis in the violent furnaces of stellar interiors or the extreme pressures of planetary cores. This was chemistry that could have occurred in environments not unlike those found on early Earth. The key to preservation appeared to be the intimate association between the sugar molecules and clay-like minerals called phyllosilicates. These mineral structures had somehow protected and stabilized the organic compounds, creating organo-mineral complexes that resisted degradation over geological timescales. It was as if the minerals had acted as molecular bodyguards, shielding their precious cargo from the destructive forces of space. Detailed mapping revealed that the sugars weren't uniformly distributed throughout the sample. Instead, they concentrated in specific regions associated with hydrated mineral veins, suggesting that their synthesis had been localized to particular microenvironments within BENNU's parent body. This heterogeneous distribution told a story of chemistry that had occurred in isolated pockets of favorable conditions. Analysis of the molecular structure revealed something even more intriguing. The sugars showed specific chirality preferences. In chemistry, many molecules can exist in two mirror image forms, like left and right hands. Biological systems strongly favor one form over the other, a phenomenon called homochirality that's essential for life. The fact that BENNU's sugars showed non-random chirality suggested that synthesis processes weren't entirely random, hinting at physical or chemical factors that could promote the emergence of biological handedness. The sugar diversity was remarkable. In addition to ribose and glucose, the samples contained traces of arabinose, xylose, and other 5- and 6-carbon sugars. This wasn't a single synthetic pathway producing one specific molecule. It was a complex chemical system generating an entire family of related compounds. The implications for understanding prebiotic chemistry were staggering. Radiometric dating pinpointed when these molecules formed, between 4.56 and 450 billion years ago, during the first 100 million years of our solar system's history. This placed their synthesis during the era of planetary accretion, when Earth was still forming from colliding planetesimals. The building blocks of life had been synthesized in space before our planet even existed as a coherent world. Laboratory experiments confirmed that sugars could indeed remain stable under space-like conditions for billions of years when properly protected by mineral matrices. Scientists reproduced the preservation conditions inferred for BENNU, demonstrating that the discoveries weren't just possible, but inevitable given the right circumstances. These findings transformed the scientific understanding of panspermia, the hypothesis that life's building blocks could travel between worlds. The discovery dramatically strengthened arguments that fundamental biological molecules could originate in space and be delivered to planets by asteroids and comets, seeding multiple worlds with the chemical precursors of life. The discoveries triggered a rush to re-examine meteorite collections in museums around the world. Within months, similar sugar molecules were identified in previously studied specimens, confirming that this complex organic chemistry had been widespread in the primitive solar system. Scientists had been sitting on evidence of extraterrestrial biochemistry for decades without realizing it. Independent laboratories across 3 continents confirmed the results. Teams in Europe, Asia, and North America all verified the presence of these molecules in their allocated samples, eliminating any possibility of experimental error or contamination. The discoveries were real, reproducible, and revolutionary. Controlled laboratory experiments successfully reproduced the synthesis of these sugars under conditions similar to those inferred for BENNU's environment. Scientists could now create ribose and glucose using the same chemical pathways that had operated in the early solar system, proving that the proposed formation mechanisms were not only plausible but highly effective. When the results were published in Nature Geoscience in December 2024, the scientific world erupted. The paper was immediately recognized as a transformative discovery that would reshape our understanding of life's origins. Within hours, researchers around the globe were redesigning experiments, revising theories, and reconsidering fundamental assumptions about how complex chemistry emerges in the universe. But as remarkable as the sugar discoveries were, they represented only the beginning of BENNU's revelations. Hidden within these ancient samples was something even more extraordinary, a substance so strange and unprecedented that it would challenge the very foundations of our understanding about what kinds of chemistry are possible in space. Dr. Scott Sanford was examining nanometer-scale fragments under his most powerful electron microscope when he encountered something that made him question his own instruments, and then his sanity. What Sanford was looking at defied every category of material science he knew. Under the microscope's beam, he could see a substance that was flexible, translucent, and behaved like nothing he had ever encountered in decades of studying extraterrestrial samples. It looked, for lack of a better comparison, like cosmic chewing gum. When he pressed the microscope's probe against the material, it deformed like soft plastic, bending and stretching in ways that should have been impossible for something that had spent billions of years in the frozen vacuum of space. But then, when he exposed it to the microscope's electron beam, essentially concentrated radiation, the material hardened, becoming rigid and brittle. This behavior had never been documented in any extraterrestrial sample. The chemical analysis results were equally baffling. This was a polymer, a long chain of repeated molecular units, but unlike any polymer found on Earth, it was extraordinarily rich in nitrogen and oxygen, with molecular bonds that seemed to form random, chaotic patterns that varied from particle to particle. Sanford's team tried for weeks to replicate this structure in their laboratory. They failed completely. What do you call something that doesn't fit into any known classification? The scientists eventually coined the term space gum, a designation that sounded almost comical but captured the bewildering nature of their discovery. This substance simply didn't belong in any existing category of mineralogy, chemistry, or materials science. Evidence suggested that this bizarre material had formed during the earliest heating phase of Bennu's parent body, approximately 4.56 billion years ago. This placed its creation at the very beginning of our solar system's history, making it one of the most primitive synthetic materials ever discovered. It was like finding a piece of cosmic manufacturing from the universe's infancy. The synthesis process, as best scientists could determine, involved reactions between ammonia, carbon dioxide, and carbonate compounds during a period of gradual heating. This had occurred before abundant liquid water altered the chemical environment. Capturing a snapshot of chemistry from the solar system's first few million years, it was primitive industrial chemistry operating on a planetary scale. Here's what made this discovery even more mind-bending. The space gum had maintained its elastic properties for over 4.5 billion years. Think about that. This material had survived cosmic radiation intense enough to sterilize planets, bombardment by micrometeoroids traveling at speeds that would vaporize steel, and temperature swings that would shatter the most durable materials we know, yet somehow it retained the flexibility to bend and deform under a microscope probe. Spectroscopic analysis revealed chemical signatures similar to terrestrial polyurethane. Scientists began calling it primitive space plastic, a cosmic polymer with a completely chaotic molecular structure that had somehow assembled itself in the early solar system. It was as if the universe had been experimenting with material science long before life evolved to do the same. The distribution of this space gum wasn't random. It concentrated in specific pockets within Bennu's matrix, as if its formation required very particular micro-environmental conditions. These weren't general chemical processes that operated everywhere. They were localized events that had created isolated deposits of this impossible material. Visually, the space gum was striking. It exhibited partial transparency with a slight yellowish tint, allowing light to pass through it in a way that reminded observers of ancient amber with fossilized insects trapped inside. But instead of preserving ancient life, this cosmic amber seemed to preserve ancient chemistry from an era before life existed. Under electron microscopy, the material revealed its true complexity. At the nanometer scale, it formed irregular three-dimensional networks filled with cavities and channels. These microscopic voids weren't random. They appeared to be systematic structures that could potentially serve as concentration sites for other molecules. Like a cosmic molecular sieve designed by chance, temperature testing revealed another impossible property. The space gum maintained its flexibility across a temperature range from -100 to +150 degrees Celsius. This meant it could remain pliable in the frozen depths of the outer solar system and in the scorching heat near Mercury's surface. No known terrestrial material exhibits such stability across such extreme conditions. Perhaps most intriguingly, the space gum demonstrated an ability to absorb and concentrate smaller organic molecules. Its porous structure acted like a molecular sponge, potentially serving as a catalyst or concentrating agent for prebiotic chemistry. This wasn't just an inert polymer, it was a potentially active participant in the chemical evolution that preceded life. Isotopic analysis confirmed what scientists already suspected. The carbon-12 to carbon-13 ratios in the space gum were significantly different from any terrestrial material, providing definitive proof of its extraterrestrial origin. This wasn't contamination from Earth-based sources. It was genuine alien chemistry. The implications were staggering. If this material could form naturally in space, it might have served as a protective matrix for preserving delicate organic molecules during interplanetary travel. Imagine complex chemistry being packaged in this cosmic bubble wrap, surviving impacts on planetary surfaces that would otherwise destroy any trace of organic compounds. The structure bore an eerie resemblance to biofilms, the protective matrices that communities of microorganisms create on Earth. Yet this space gum was entirely abiotic, formed through purely chemical processes without any biological intervention. It raised fascinating questions about whether chemistry and biology might converge on similar solutions to similar problems. Laboratory experiments revealed that, when exposed to water, the space gum slowly released nitrogen-rich compounds. These weren't random degradation products. They were potentially useful chemical nutrients that could fuel further prebiotic chemistry in aqueous environments. The space gum wasn't just preserving ancient chemistry. It might be actively contributing to new chemistry when conditions were right. The material showed extraordinary resistance to chemical attack. Acids, bases, and organic solvents that would dissolve most known polymers barely affected the space gum. This exceptional durability explained how it had survived billions of years of exposure to the harsh chemical environment of space, maintaining its structure when everything around it was being altered by cosmic weathering. What did this discovery mean for our understanding of prebiotic chemistry? If complex polymers could form spontaneously in the early solar system and remain stable for geological time periods, it suggested that the universe might be far more chemically creative than we had ever imagined. The space between the stars wasn't just empty void, it was a vast laboratory where exotic chemistry could unfold on timescales that dwarfed human civilization. The space gum represented something unprecedented in cosmic materials science. It was a completely new category of matter that challenged established theories about what kinds of chemical processes were possible in the primitive solar system. Scientists would have to revise their models of early planetary formation to account for this level of complex chemistry occurring in environments they had assumed were too simple for such sophisticated molecular architecture. Yet, as extraordinary as the space gum was, it represented just another layer in BENNU's growing catalogue of impossibilities. This ancient asteroid was revealing itself to be far more than a simple collection of cosmic debris. It was a chemical archive that preserved evidence of processes that seemed to operate on the very edge of what physics and chemistry should allow, and still, BENNU had more secrets to reveal. Deep within its matrix lay evidence of yet another impossible preservation, tiny grains of matter that predated our solar system itself, carrying the signatures of stellar explosions from an era before our sun had even begun to shine. When Dr. Larry Nittler began analyzing the microscopic components of BENNU's samples, he discovered something that defied all expectations. The asteroid contained 6 times more pre-solar material than any extraterrestrial sample ever studied. These weren't just ancient particles. These were relics from stars that had lived, evolved, and died before our sun was even a glimmer in a cosmic gas cloud. Each grain was a messenger from the deep past, carrying within its crystal structure the isotopic signatures of nuclear furnaces that had burned out billions of years before Earth existed. Think about the scale of what we're discussing here. Each pre-solar grain measures between 50 nanometers and 2 micrometers, so incredibly small that thousands of them could fit within the thickness of a single human hair. Yet within these microscopic particles lies preserved evidence of stellar processes that occurred when our galaxy was young, when the chemical elements that would eventually form our solar system were still being forged in the hearts of dying stars. The majority of these ancient grains consist of silicon carbide, an extremely durable crystal that formed in the atmospheres of carbon-rich giant stars. This material is so resilient that it survived the violent death throes of its parent stars, the turbulent collapse and reformation of the solar nebula, and billions of years of cosmic bombardment. It's essentially indestructible on astronomical timescales. The formation conditions for these grains boggle the mind. They crystallized at temperatures exceeding 2,000 degrees Celsius in the outer atmospheres of dying stars, condensing from stellar winds like cosmic snowflakes in a furnace. Each grain carries within its crystal lattice the thermal memory of nuclear fires that burned with the energy of hundreds of billions of suns. Radiometric dating of individual grains revealed ages between 4.7 and 7 billion years. This means some of these particles are older than our galaxy in its current spiral configuration. They formed when the Milky Way was still a chaotic collection of star-forming regions. Before the elegant spiral arms we see today had organized themselves across hundreds of millions of years of galactic evolution. Here's what makes their preservation in BENNU absolutely remarkable. These pre-solar grains are extraordinarily fragile, easily destroyed by chemical alteration or thermal processing, yet they survived intact despite BENNU having experienced extensive hydrothermal activity that completely transformed the surrounding mineral matrix. Somehow, these ancient particles found protection in specific microenvironments that preserved them like insects in amber. Isotopic analysis revealed something that sent shockwaves through the astronomical community. The grains showed contributions from at least 12 different types of stars, including supernovae of various masses and red giant stars with dramatically different chemical compositions. BENNU wasn't just preserving stardust from one or two stellar sources, it was a repository of stellar death from across an entire region of the ancient galaxy. Many grains contained elements like iron-60 and aluminum-26, radioactive isotopes with half-lives so short they could only exist if the grains had formed very close to supernova explosions. This was direct, physical evidence that our solar system had formed in a stellar nursery that was being actively enriched by multiple stellar explosions. We were holding proof that our cosmic neighborhood had been a violent, dynamic place during the solar system's birth. The distribution of pre-solar grains wasn't uniform throughout BENNU. Concentrations varied dramatically between different regions of the samples, suggesting that their incorporation had been a localized, episodic process rather than uniform mixing. This heterogeneity told a story of complex dynamics in the solar nebula, where stellar materials were stirred unevenly like ingredients in a cosmic soup. What's truly extraordinary is that these delicate grains survived processes that completely altered the minerals around them. While phyllosilicates, carbonates, and other minerals were being transformed by hydrothermal activity, the pre-solar grains remained perfectly intact. They demonstrated stability against recrystallization and atomic diffusion that challenged our understanding of materials science. The isotopic signatures were so distinctive that scientists could identify contributions from individual stellar explosions. Different supernova events leave characteristic fingerprints in the ratios of various isotopes, allowing researchers to trace specific grains back to specific stellar deaths. BENNU contained evidence of multiple supernovae that had exploded in our cosmic neighborhood billions of years ago. The age distribution of the grains revealed the timeline of stellar enrichment that preceded our solar system's formation. Material from stellar deaths had been accumulating in the interstellar medium for millions of years before the gravitational collapse that would eventually form our sun and planets. The solar nebula had been slowly cooking in a stew of stellar debris for eons before planetary formation began. Some of the oldest grains may have originated in completely different regions of the galaxy, Stars with different formation histories and chemical evolution paths contributed to the mix, suggesting that galactic-scale processes had transported material across vast distances before it became incorporated into our solar system. We were holding evidence of cosmic migration spanning hundreds of light years. The pre-solar grains appeared to be encapsulated in organic material that had protected them for billions of years. This suggested a kind of symbiosis between the inorganic stellar relics and the organic chemistry that would eventually give rise to life. The universe seemed to have developed natural preservation systems that maintained both stellar and biological heritage. Different types of grains had condensed under different temperature conditions in their parent stellar atmospheres. This provided a suite of stellar thermometers, allowing scientists to reconstruct the physical conditions in the outer layers of dying stars from billions of years ago. Each grain type told part of the story of how elements heavier than hydrogen and helium were synthesized and dispersed throughout the galaxy. The simultaneous presence of grains from such diverse stellar origins provided evidence of efficient mixing in the primitive solar nebula. Traditional models had suggested relatively static conditions during planetary formation, but the pre-solar grain evidence pointed to much more dynamic, turbulent processes that could thoroughly stir materials from different stellar sources across the disk. The surfaces of these ancient grains may have served as nucleation sites for complex organic molecule synthesis. Their crystalline structures could have provided the organizational templates needed for carbon-based chemistry to develop complexity, potentially serving as the interface between purely inorganic stellar processes and the organic chemistry that would eventually lead to life. The grains preserved records of cosmic ray damage accumulated during their interstellar journeys. By studying the radiation damage patterns, scientists could calculate how long these particles had traveled through space before being incorporated into the solar system, providing chronometers for galactic-scale transport processes. The collection of pre-solar grains in BENNU represented the most diverse and well-preserved sample of pre-solar system material ever obtained for laboratory study. It was like having a library of stellar death certificates from the early galaxy. Each grain a book that told the story of a star's final moments and the chemical legacy it left behind. As remarkable as these individual discoveries were, the complex sugars, the impossible space gum, the ancient stellar debris, they were all building towards something even more profound. Taken together, these findings were revealing that BENNU wasn't just a random collection of cosmic debris, but something far more significant and disturbing. By early 2025, as laboratories around the world continued their analysis, scientists began to realize they weren't just looking at unusual chemistry. They were confronting a convergence of impossibilities that challenged the very foundations of what we thought we knew about how matter behaves in space. Consider what BENNU was simultaneously preserving: complex sugars that should have decomposed billions of years ago, a flexible polymer that defied materials science, and the largest concentration of pre-solar grains ever found in a single object. Each discovery by itself was remarkable. Together, they represented a combination that violated fundamental principles of chemistry and physics. The mathematical probability of this convergence was staggering, according to established kinetic models. Organic molecules like ribose and glucose should decompose completely when exposed to cosmic radiation over timescales millions of times shorter than BENNU's age. The statistical likelihood of finding them intact after 4.6 billion years in space was less than 1 in 10 trillion, yet there they were, perfectly preserved and chemically active. The degradation laws that govern molecular stability weren't suggestions. They were fundamental constraints based on quantum mechanics and thermodynamics. Cosmic radiation breaks chemical bonds with ruthless efficiency. Temperature cycling causes thermal expansion and contraction that should shatter molecular structures. The space environment is essentially a molecular death sentence for complex organic compounds. But somehow, BENNU had found ways to circumvent these universal principles. The chemical environment preserved in BENNU was internally contradictory in ways that shouldn't be possible. Evidence showed the asteroid had simultaneously experienced oxidizing and reducing conditions, wet and dry environments, high and low temperatures. According to geochemical models, these conditions were mutually exclusive. You can't have strongly oxidizing minerals forming in the same space and time as strongly reducing ones. Yet BENNU contained both, side by side. As if different regions had experienced completely different chemical histories while remaining physically connected. The synthesis of complex molecules in the vacuum of space presented another layer of impossibility. Laboratory chemistry requires carefully controlled conditions, specific pressures, temperatures, and chemical concentrations to produce molecules like those found in BENNU, the chaotic environment of the early solar system. With its temperature extremes and near-vacuum conditions, should have prevented rather than promoted complex molecular synthesis. The space gum represented perhaps the most egregious violation of thermodynamic principles. According to fundamental physical laws, this polymer should have spontaneously decomposed into simpler, more stable components within geological timescales. Instead, it existed in what appeared to be a state of impossible equilibrium, maintaining its complex structure against all thermodynamic pressures. To simplify, cosmic radiation damage analysis revealed another paradox. Organic molecules exposed to the cosmic ray environment for billions of years should exhibit extensive fragmentation and cross-linking damage. Instead, spectroscopic analysis showed molecular structures that were surprisingly intact, as if they had been shielded by some unknown protective mechanism that operated more efficiently than any known physical process. The thermal history of BENNU created yet another impossibility. The asteroid showed clear evidence of having experienced heating sufficient to alter mineral structures and drive off volatile compounds. This same heating should have destroyed any organic molecules present. Yet the organic compounds not only survived, but appeared to have formed during the heating episodes. The physics simply didn't add up. Mineralogical analysis revealed the coexistence of phases that were thermodynamically incompatible. Minerals that form under strongly oxidizing conditions existed immediately adjacent to minerals that require strongly reducing environments. According to chemical equilibrium principles, these phases should react with each other until one or the other disappears. Instead, they had coexisted peacefully for billions of years. The spatial distribution of organic compounds defied every known mechanism for chemical segregation. Sugars and polymers had concentrated in specific regions with surgical precision, creating chemical gradients that required selective transport processes. No known physical mechanism could achieve such selective molecular concentration in the absence of biological systems or sophisticated laboratory equipment. Chirality preservation presented another fundamental violation of chemical principles. Chiral molecules naturally racemize over time, converting from one-handedness to a random mixture of both forms. This process occurs rapidly on geological timescales, especially under the harsh conditions of space. Yet BENNU's molecules retained their specific chirality preferences after billions of years, as if the normal rules of stereochemistry had been suspended. The formation of long-chain polymers in the primitive solar system environment challenged everything known about polymerization chemistry. Creating stable polymer chains requires controlled conditions that simply didn't exist in the chaotic early solar system. Instead of polymerization, the dominant processes should have been molecular fragmentation and decomposition. Yet BENNU contained evidence of sophisticated polymer synthesis occurring in an environment that should have prevented it. The organic molecules exhibited stability that required protective mechanisms completely unknown to current chemistry. The preservation wasn't just good, it was perfect, suggesting intervention by processes that operated with an efficiency that exceeded any known natural phenomenon. It was as if BENNU had access to molecular preservation technology that surpassed human scientific understanding. Chemical gradients on micrometer scales required differentiation processes that couldn't operate in a body of BENNU's size. Creating distinct chemical zones typically requires large-scale melting and differentiation, processes that would completely destroy organic compounds. Yet BENNU showed evidence of fine-scale chemical differentiation that had occurred without destroying its delicate molecular cargo. Isotopic signatures throughout the samples required formation environments that were mutually exclusive. Some components showed isotopic ratios consistent with formation in the inner solar system, while others required outer solar system conditions. Still, others demanded interstellar environments. According to physics, these materials couldn't have formed in the same object unless fundamental assumptions about planetary formation were completely wrong. The crystallization of minerals within organic matrices violated basic principles of crystal growth. Inorganic crystals normally cannot form properly in the presence of organic polymers, which interfere with crystal lattice development. Yet BENNU showed perfect crystal formation that had somehow occurred in intimate association with complex organic compounds, creating hybrid structures that shouldn't exist. Multiple generations of chemical alteration had occurred without destroying earlier formed components. Evidence pointed to at least 3 distinct episodes of chemical modification, each of which should have obliterated the products of previous episodes. Instead, they had accumulated like geological layers, preserving a complete history of chemical evolution that defied normal patterns of mineral alteration. The overall chemical system exhibited emergent complexity that arose spontaneously without any directing mechanism. Complex molecular organization typically requires either biological systems or intelligent design to overcome thermodynamic barriers to organization. Yet BENNU's chemistry showed sophisticated organizational patterns that had emerged through purely natural processes, suggesting possibilities that transcended current understanding of how complex systems form. Perhaps most troubling of all, the combined discoveries from BENNU forced scientists to confront the possibility that their fundamental understanding of chemistry, physics, and planetary formation was incomplete. The asteroid wasn't just preserving unusual chemistry, it was documenting processes that operated according to principles that remained unknown to science. As the full scope of these impossibilities became clear, researchers realized they weren't just studying an unusual asteroid. They were confronting evidence that the universe was far more chemically creative and physically sophisticated than anyone had imagined, operating according to principles that human science was only beginning to glimpse. The truth, when it finally emerged from months of analysis and debate, was more revolutionary than anyone had dared imagine. BENNU wasn't simply a primitive asteroid that had accidentally preserved some interesting chemistry. It was the remnant of something far more significant, a natural laboratory that had operated on a cosmic scale during the formation of our solar system. The evidence was undeniable once scientists stepped back and looked at the complete picture. BENNU represented the surviving fragment of a chemical reactor that had functioned for hundreds of millions of years, synthesizing molecules of impossible complexity through processes that current science couldn't explain. This wasn't random cosmic chemistry. This was systematic, almost purposeful molecular engineering operating on geological timescales. The discoveries suggested that the synthesis of life's fundamental building blocks wasn't a rare accident unique to Earth. Instead, it appeared to be a common process that occurred spontaneously in space environments under specific conditions that scientists were only now beginning to understand. The universe wasn't just physically creative, it was biochemically inventive on a scale that dwarfed human imagination. BENNU's parent body had functioned as a gigantic natural reactor, maintaining stable chemical conditions for hundreds of millions of years. Think about the engineering implications of that. This small world had somehow sustained complex chemical processes longer than multicellular life had existed on Earth, operating with a consistency and efficiency that rivaled the most sophisticated human laboratories. The material preserved in BENNU represented something unprecedented in our understanding of chemistry and biology. It was a bridge state between purely inorganic chemistry and biological processes, suggesting that the transition from non-life to life might be far more gradual and inevitable than scientists had ever imagined. The gap between chemistry and biology wasn't a chasm to be crossed. It was a continuum to be explored. BENNU had become a molecular archive, preserving chemical recipes from the primitive solar system that Earth had long since lost. While our planet's active geology had recycled and transformed its original chemical signatures beyond recognition, this small asteroid had maintained a perfect library of primordial molecular information. It was like discovering an intact ancient library in a world where all other books had been destroyed. The conditions that had enabled this extraordinary chemistry were becoming clearer. Low gravity had allowed delicate structures to form without being crushed by their own weight. The asteroid's position had provided just enough radiation shielding to prevent molecular destruction, while still driving chemical reactions. Gradual heating had created a perfect thermal environment for complex synthesis without the violent temperatures that would have destroyed delicate products. The interaction between clay minerals and organic compounds had created something revolutionary. A self-sustaining catalytic system that promoted increasingly complex molecular synthesis over geological time. The minerals hadn't just preserved the organic compounds, they had actively facilitated their formation and evolution, creating hybrid organomineral systems that operated with an efficiency that exceeded purely biological processes. The cosmic chemistry revolution. BENNU's revelations, perhaps most remarkably. The chemical processes discovered within BENNU demonstrated characteristics that fundamentally challenged our understanding of evolution itself. Like biological systems engaged in selective pressure, the chemistry appeared to actively favor molecules that exhibited greater complexity and enhanced stability, as if invisible forces were operating even in purely chemical environments to guide molecular development toward increasing sophistication. This wasn't random chemistry producing arbitrary results through chance encounters. This was systematic, directed synthesis, where the universe itself seemed to be conducting experiments in molecular complexity. The implications suggested that evolution might not represent a uniquely biological phenomenon emerging only after life began, but rather a fundamental property of complex systems operating at every scale of cosmic organization. From stellar nucleosynthesis to planetary formation to the emergence of consciousness itself, the space gum phenomenon might represent a universal solution to one of astrobiology's most persistent and challenging questions. How do delicate organic molecules, fragile arrangements of carbon and hydrogen and oxygen that would normally decompose under the slightest stress, survive the absolutely brutal journey between worlds across millions of years of cosmic radiation? Temperature extremes that swing from near absolute zero to scorching heat, and the violent mechanical forces of gravitational encounters and impact events. This cosmic polymer could represent nature's own engineered answer to interplanetary protection, a naturally occurring packaging and preservation system that allowed the most complex chemistry to travel safely across vast distances throughout the solar system, seeding multiple worlds simultaneously with identical molecular ingredients for life, creating a connected network of chemical evolution that spanned planetary scales. The specific chemical conditions preserved within BENNU's interior revealed an environment that was in many ways more favorable for sophisticated organic chemistry than the harsh conditions that characterized early Earth. The precise temperature ranges, the carefully balanced pH levels, the optimal ionic concentrations, and the controlled water availability had collectively created an environment that approached the ideal conditions for prebiotic synthesis, suggesting that small asteroids might actually function as superior nurseries for complex chemistry compared to the chaotic, violent, and unstable conditions that characterize planetary surfaces during the early solar system. These small rocky bodies offered protection from radiation, stable temperatures over geological time, and the perfect chemical cocktail for molecular experimentation on scales that dwarfed any laboratory humans had ever constructed. Multiple independent chemical pathways operating simultaneously within the asteroid had converged on identical molecular products through completely different synthetic routes. This represented something far more significant than accidental chemistry producing random results through statistical inevitability. This was evidence of systematic synthesis, where entirely different chemical processes, operating under different conditions and using different starting materials, consistently led to the same complex molecular outcomes, strongly suggesting that certain sophisticated molecules represented inevitable products of cosmic chemistry rather than unlikely accidents. Ribose, glucose, amino acids, and the other complex compounds discovered in BENNU might represent universal chemical constants, molecules that emerge naturally whenever the right conditions exist anywhere in the universe, making them as fundamental to cosmic evolution as hydrogen and helium. The specific molecular arrangements preserved within BENNU's chemical archive contained unprecedented information about the physical and chemical conditions that existed in the protoplanetary disk during the earliest stages of solar system formation. These weren't simply chemical fossils preserving ancient molecular structures. They were detailed environmental records that documented temperature variations, pressure fluctuations, chemical composition changes, and countless other environmental factors during planetary formation, recorded with an accuracy and resolution that no other geological or astronomical process could possibly achieve. Each molecule told a story about cosmic conditions that existed billions of years before Earth had even begun to form, creating a chemical library that preserved the complete history of our solar system's birth. BENNU represented far more than just another asteroid containing organic molecules. It provided a comprehensive model for understanding how life might emerge in small rocky bodies throughout the universe. The asteroid demonstrated conclusively that complex prebiotic chemistry doesn't require Earth-like planets with their specific combinations of atmospheric composition, surface pressure, and gravitational conditions. Instead, moons orbiting gas giants, asteroids drifting through the outer solar system, comets carrying ancient ice, and countless other small worlds previously dismissed as too harsh for biological processes, might all serve as potential cradles for the chemical evolution that precedes biology, vastly expanding the number of potentially habitable environments that exist throughout the universe by orders of magnitude. The simultaneous presence of all fundamental RNA components within a single extraterrestrial object provided definitive proof that life's essential building blocks represented inevitable products of cosmic chemical evolution rather than extraordinary coincidences. This discovery wasn't merely remarkable or surprising. It constituted irrefutable evidence that the universe naturally and consistently synthesizes the complete molecular toolkit required for biology to emerge. The ingredients for life weren't rare cosmic accidents that occurred only under the most exceptional circumstances, but common, predictable products of the stellar nucleosynthesis and planetary formation processes that operate throughout the galaxy, meaning that the chemical foundation for life exists everywhere that stars form and planets condense. The revolutionary timeline revealed by BENNU's chemical archive extended the history of complex molecular evolution by hundreds of millions of years beyond previous estimates. Complex chemical evolution had been operating continuously for vast periods before Earth had even finished accreting from the solar nebula, providing life with far more time to emerge and evolve than any traditional models had ever suggested possible. This extended timeline meant that the universe had been actively preparing for biology, conducting chemical experiments and synthesizing molecular toolkits for geological ages before planets had become stable enough to host the transition from chemistry to life, fundamentally altering our understanding of how long biological processes have been operating in the cosmos. Asteroids like BENNU had functioned as components of a vast distribution network, systematically spreading identical packages of complex molecules throughout the entire solar system over millions of years. They represented cosmic delivery vehicles that had seeded multiple worlds, from Mercury to Mars to the moons of the outer planets, with chemically identical packages of prebiotic materials, creating an interconnected web of molecular evolution that linked every planet and moon in our solar system through shared chemical heritage. Life's origins weren't isolated to Earth as a unique planetary phenomenon, but represented a system-wide process that operated on solar system scales, making biology a collective property of planetary systems rather than individual worlds. The chemistry demonstrated remarkable self-organizational capabilities that were previously thought to be exclusively characteristic of biological systems. Complex molecular structures had assembled themselves spontaneously from simpler components, creating organized patterns and sophisticated functional arrangements without any external guidance or intervention, purely through the operation of chemical forces and thermodynamic principles. This suggested that the traditional boundary between non-living chemistry and living biology was far more blurred and permeable than anyone had ever realized, with chemical systems naturally evolving toward the complexity and organization that we associate with life itself. Most profound of all, the discovery that sophisticated molecular complexity had existed in cosmic environments before Earth had even formed completely revolutionized our understanding of life's place in cosmic evolution. This meant that biology might not represent an unlikely emergence from simple chemistry through billions of years of gradual development, but rather the natural continuation of chemical evolution that had been operating on cosmic scales for far longer than Earth's entire history. Biology wasn't separate from cosmology or somehow independent from cosmic processes. It represented the inevitable expression of universal evolutionary tendencies that operate at every scale, from molecular to galactic, making life not an accident, but a fundamental feature of cosmic development. BENNU forced a radical expansion of scientific concepts about where and how life could potentially emerge throughout the universe. Not just on Earth-like planets orbiting sun-like stars in narrow habitable zones, but in asteroids drifting through interplanetary space, on icy moons orbiting gas giants, in comets carrying ancient water and organics, and in countless other environments that had previously been dismissed as too harsh, too cold, too small, or too chemically simple to support the sophisticated processes that lead to biology. The universe was revealing itself to be far more hospitable to life at every scale, from molecular to planetary, than anyone had ever imagined possible. The discoveries established the foundation for a completely new era in astrobiology. Instead of searching exclusively for liquid water and Earth-like atmospheric and surface conditions as indicators of potential habitability, scientists would now focus primarily on detecting complex prebiotic chemistry as the fundamental signature of environments where life might emerge. The chemical signatures of life's potential might be written in molecular complexity and preserved in rocky materials for billions of years before biology itself ever emerged, creating entirely new methodologies for searching for life's potential throughout the universe, from nearby asteroids to exoplanets orbiting distant stars. But what did all of these revolutionary discoveries truly mean for us as human beings? What did these profound revelations about cosmic chemistry and universal molecular evolution mean for humanity's understanding of its own nature and place in the universe? The implications strike directly at the very core of human identity and our understanding of what we are. If the fundamental ingredients of life arrived on Earth through asteroid bombardment, similar to what we observe in BENNU, then every human being walking the planet today is literally constructed from stardust that underwent sophisticated chemical processing in cosmic laboratories, operating billions of years before our planet had even finished forming. We are not just made of star stuff, as Carl Sagan famously observed decades ago. We're made of star stuff that underwent incredibly sophisticated chemical processing in space-based molecular factories operating on geological timescales that dwarf human comprehension, making us direct products of cosmic chemistry rather than planetary evolution. Consider this profound and staggering truth about your own physical existence. Every carbon atom currently forming the structure of your body, every oxygen molecule you breathe, every trace element in your blood, may have passed through chemical processes that were identical to those discovered operating within BENNU's molecular laboratories. The glucose molecules powering your brain's thoughts right now, the ribose forming the fundamental backbone of your RNA, the complex polymers that provide structure to every cell in your body. All of these sophisticated biological molecules might be direct descendants of chemical products that were synthesized in small rocky worlds drifting through the primitive solar system billions of years before Earth existed. Your biology isn't separate from cosmic evolution. It represents the direct continuation of chemical processes that began operating in space long before planets had even finished forming. Think carefully about what this means for the most mundane aspects of your daily existence. The sugar you add to your morning cup of coffee underwent molecular pathways that were first established and perfected in asteroid laboratories 4.6 billion years ago. The caffeine molecules that stimulate your neurons and enhance your alertness follow chemical architectures that were prototyped and tested in the cosmic void before Earth had even begun to solidify. Every breath you take, every heartbeat that sustains your life, every thought that passes through your consciousness, all powered by sophisticated chemistry that was perfected in space-based laboratories, operating for hundreds of millions of years before planetary surfaces became stable enough to host life. These discoveries suggest that the emergence of life throughout the universe isn't an extraordinary accident limited to Earth or other rare oasis worlds scattered throughout an otherwise sterile cosmos. Instead, life appears to represent a natural and perhaps inevitable consequence of universal chemical evolution that operates wherever the appropriate conditions exist. This means we're not cosmic anomalies clinging desperately to a rare habitable world in a universe that's hostile to life. We're natural expressions of fundamental evolutionary processes that operate consistently throughout the cosmos, making life not just possible, but highly probable wherever small rocky bodies can maintain the chemical conditions necessary for molecular complexity to develop and evolve. This discovery completely transforms our scientific understanding of habitability throughout the universe. Small rocky bodies, including asteroids circulating through planetary systems, moons orbiting gas giant planets, and comets carrying ancient ice and organics from the outer reaches of stellar systems, might prove far more important for astrobiology than Earth-like planets with their specific atmospheric and surface conditions. These smaller objects could serve as the primary nurseries for prebiotic chemistry throughout the galaxy, systematically seeding larger worlds with the molecular ingredients required for life to emerge. Meaning that the traditional concept of habitable zones around stars might need to be completely reconceptualized to include the entire volume of space, where small bodies can maintain stable conditions for complex chemistry to develop. Future space exploration missions will need to fundamentally reprioritize their scientific objectives, placing asteroids and comets at the center of efforts to detect and study advanced prebiotic chemistry. Instead of focusing exclusively on Mars, with its ancient riverbeds and polar ice caps, or the icy moons of Jupiter and Saturn with their subsurface oceans, astrobiologists should be planning comprehensive sample return missions to dozens of carefully selected small bodies throughout the solar system. Each asteroid represents a potential chemical time capsule that might preserve different stages and pathways of prebiotic evolution, offering unprecedented windows into molecular processes that operated continuously for hundreds of millions of years before Earth became habitable, creating an archive of cosmic chemical history that spans the entire formation period of our solar system. The temporal implications of these discoveries are absolutely staggering in their scope. If sophisticated chemical complexity preceded planetary formation by hundreds of millions of years, then life itself had access to far more evolutionary time to emerge and develop than any traditional estimates had ever suggested possible. This dramatically extended timeline means that biological evolution, and even the emergence of intelligence and consciousness, could have occurred much earlier in cosmic history than we previously thought possible, with profound implications for our ongoing search for extraterrestrial civilizations throughout the galaxy. The universe might be far older in biological and evolutionary terms than we ever dared imagine, meaning that intelligence could have emerged billions of years earlier than Earth-based models predict. The discovery of specific complex sugars like ribose and glucose preserved in space provides strong evidence that terrestrial biochemistry might reflect universal chemical trends that operate throughout the galaxy. This means that extraterrestrial life, when we eventually discover and study it, might prove more biochemically familiar than we ever dared hope. The fundamental molecular machinery that powers life, including energy storage and transfer systems, information processing and storage molecules, and the structural polymers that provide cellular architecture, might represent universal constants of cosmic chemistry rather than Earth-specific evolutionary accidents, making life throughout the universe potentially far more similar to terrestrial biology than decades of speculation about exotic biochemistries had suggested. The remarkable ability of organic molecules to survive, essentially unchanged for billions of years in space environments, suggests that detailed records of primitive life and early evolutionary stages could be preserved indefinitely in rocky bodies throughout the galaxy. Ancient asteroids and comets circulating through mature planetary systems might serve as biological museums and archives, maintaining perfect records of evolutionary chemistry from billions of years ago that document the complete pathway from simple molecules to complex biology. We might eventually be able to study the detailed history of life's emergence not just on Earth, but across multiple star systems, reconstructing the universal chemical evolution that preceded biology on worlds we'll never visit, creating a galactic perspective on life's origins and development. The accumulating evidence strongly supports the concept of chemical panspermia, the idea that life's fundamental building blocks travel regularly between worlds and even between stellar systems, creating a vast galactic network of molecular exchange that connects planetary systems across enormous distances through shared chemical heritage. Life's origins become not just a local planetary phenomenon, but part of a cosmic web of chemical evolution that spans the entire galaxy, meaning that every world that eventually develops biology does so using molecular tools and chemical pathways that were shared across interstellar distances, making life a collective galactic property rather than an isolated planetary accident. For future space colonization efforts, these discoveries reveal that asteroids rich in complex organic molecules could provide resources that extend far beyond simple fuel, water, and metallic minerals. They could serve as concentrated sources of biologically relevant compounds that would prove essential for establishing and maintaining closed-loop life support systems in space. Future space settlers might mine asteroids not just for conventional resources, but specifically for the chemical building blocks of life itself, using molecules that were synthesized in space billions of years before humans existed to create sustainable ecosystems that support permanent human presence throughout the solar system and eventually beyond. The story of early Earth's development needs to be completely rewritten based on these discoveries. Our planet didn't gradually develop complex chemistry from simple beginnings through billions of years of slow, incremental molecular evolution operating in isolation. Instead, Earth received a constant bombardment of sophisticated organic molecules delivered from space that dramatically accelerated the transition from simple, inorganic chemistry to the complex prebiotic systems that eventually gave rise to life. The emergence of biology on Earth might have been jump-started by systematic chemical seeding from space that delivered pre-assembled molecular toolkits, making Earth's biological development far more rapid than traditional models suggested possible. Millions of asteroids throughout our solar system might currently be conducting chemical experiments similar to those that created BENNU's remarkable molecular treasures. This means our solar system contains a vast, distributed network of natural laboratories, each potentially developing unique chemical solutions to the fundamental challenges of molecular complexity and self-organization. We're literally surrounded by cosmic chemistry sets operating on scales that completely dwarf human research capabilities, conducting experiments that span geological time periods, and producing results that could revolutionize our understanding of chemistry, biology, and the emergence of life throughout the universe. If BENNU preserves such remarkable chemical complexity after billions of years, other asteroids circulating through our solar system and beyond might contain evidence of even more advanced stages of chemical evolution. Some might preserve proto-organismal structures or sophisticated chemical systems that closely approach the blurred boundary between pure chemistry and true biology. Future sample return missions could potentially discover molecular stepping stones that trace the complete evolutionary pathway from simple cosmic chemistry to fully organized living systems, revealing intermediate stages of development that Earth's active geology has long since erased from our planetary record. These revolutionary discoveries force us to completely revise our estimates for biological and evolutionary timelines throughout the universe. If molecular complexity preceded life by such vast periods of time, then biological evolution itself might proceed far more rapidly than traditional Earth-based models have predicted. Intelligence and consciousness could emerge on much shorter timescales than we currently believe possible, making the universe potentially alive with thinking beings that emerged from this universal chemical foundation far earlier and more frequently than anyone has imagined, fundamentally changing our expectations about the prevalence of intelligence throughout the cosmos. From a broader philosophical perspective, humanity emerges not as an isolated miracle or cosmic accident, but as a natural expression of chemical processes that operate on truly universal scales throughout space and time. This positions our existence as participants in rather than mere observers of cosmic development, making us local manifestations of universe-scale evolution that connects our origins directly to the fundamental processes that govern stellar formation, planetary development, and the emergence of complexity at every scale of cosmic organization. As products of this universal chemical evolution, humans carry a unique responsibility to preserve and systematically study the chemical records preserved in other worlds throughout our solar system and beyond. We're not just explorers seeking resources or knowledge for our own benefit. We're custodians of cosmic heritage with the responsibility to understand and protect the chemical archives that document the universe's billions-year journey toward increasing complexity and the eventual emergence of life and consciousness. Every asteroid we study, every sample we carefully preserve and analyze, contributes to humanity's growing understanding of its own cosmic origins and our fundamental connection to universal evolutionary processes. The discovery that all RNA components exist naturally in space environments suggests that purely RNA-based life might actually exist and operate in space itself, independent of planetary surfaces or traditional biological environments. This would represent a completely different form of biology, potentially more primitive than DNA-based terrestrial life, but also far more adaptable to the extreme conditions that characterize most of the universe. We might need to dramatically expand our definitions of life to include sophisticated chemical systems that exist and evolve in the vacuum of space itself, operating on timescales and in environments that challenge every assumption about what life requires to emerge and survive, opening entirely new avenues for discovering life throughout the cosmos. Every molecule in your body connects you to chemical processes that have operated across cosmic distances and billion-year timescales. The atoms that form your DNA were forged in stellar cores, processed in interstellar space, refined in cosmic laboratories like BENNU, and delivered to Earth by asteroid impacts billions of years ago. You're not just a biological being, you're a living archive of cosmic chemical history, a conscious expression of processes that began before our solar system existed. These revelations provide powerful scientific motivation for extensive exploration of small bodies throughout the solar system and beyond. Every asteroid, comet, and minor planet represents a potential repository of chemical evolution that could reveal new chapters in the story of how complexity emerges from simplicity. The scientific treasures waiting in these small worlds could revolutionize our understanding of life's place in the universe and our own position in the cosmic story. Ultimately, Humans emerge not as cosmic anomalies, but as local expressions of chemical and evolutionary processes that operate on galactic scales. We are part of a vast, interconnected web of cosmic evolution that links us to every star, every planet, and every chemical process that has operated since the universe began forming complex structures. Our existence becomes not a miracle, but an inevitability, the natural result of a universe that has been evolving toward complexity, consciousness, and perhaps something even more extraordinary that we're only beginning to glimpse. And now, as we stand at the threshold of understanding these revelations, we must ask ourselves, what kind of future does this new reality create for humanity? The universe has revealed itself to be not a cold, sterile void punctuated by rare islands of complexity, but a vibrant chemical laboratory where molecular sophistication emerges spontaneously across cosmic distances and geological time. BENNU has fundamentally transformed our perception of space itself. Every cubic meter of the cosmos is potentially alive with chemical creativity, operating experiments in molecular architecture that dwarf human scientific capabilities. The emptiness between stars isn't empty at all. It's a vast workshop where the universe has been crafting the ingredients for consciousness for billions of years. We're looking at the emergence of a galactic molecular library. Each asteroid, comet, and rocky fragment throughout our galaxy may preserve unique chapters of cosmic chemical evolution, creating a distributed archive that contains 8 billion years of universal history written in molecular languages we're only beginning to learn to read. This library spans distances that light takes millions of years to cross, with each volume containing chemical information that could revolutionize our understanding of how complexity emerges from simplicity on cosmic scales. The next decades will witness an explosion of sample return missions targeting small bodies throughout the solar system. Every returned sample will offer new insights into prebiotic chemistry and biological potential that could reshape our understanding of life's possibilities. We're entering an era where chemical archaeology becomes as important as traditional archaeology. But instead of uncovering human history, we'll be excavating the molecular heritage of the cosmos itself. Each mission will be like opening another book in this cosmic library, revealing chapters of chemical evolution that Earth's geological activity has long since erased. Understanding how BENNU synthesized complex molecules under space conditions could revolutionize industrial production on Earth. The asteroid demonstrated chemical processes that operate with remarkable efficiency under conditions that would challenge the most sophisticated human laboratories. Imagine manufacturing systems that work in near-vacuum conditions, that harness solar radiation for energy, that operate for millions of years without maintenance. By learning to replicate these cosmic synthesis pathways, we might develop manufacturing processes that are more sustainable, efficient, and capable of producing molecular structures we've never been able to create. The unique molecules discovered in BENNU's samples could inspire entirely new approaches to medicine. Compounds that demonstrate exceptional stability against degradation over billions of years might hold keys to developing drugs that remain effective longer, or protective agents that could shield human cells from damage during long-duration space travel. The space gum alone represents a class of materials that could revolutionize drug delivery systems, creating protective matrices that release therapeutic compounds over controlled timeframes. The universe has been conducting pharmaceutical research for billions of years. We just need to learn to read its results. Complex organic compounds from asteroids could form the foundation for extraterrestrial agriculture. As humanity expands into space, These cosmic nutrients could provide the chemical building blocks needed to establish closed-loop ecosystems that support human colonies on distant worlds. Instead of shipping biological materials from Earth at enormous cost and risk, future space settlers might harvest the molecular tools for life directly from local asteroids. Entire agricultural systems could be bootstrapped from the chemical complexity that already exists in space. The preservation techniques demonstrated by BENNU could inspire revolutionary methods for long-term storage of biological and cultural information. If cosmic processes can maintain molecular integrity for billions of years, perhaps we can develop analogous systems to preserve human knowledge, genetic diversity, or even consciousness itself across geological timescales. Imagine libraries that could survive the death of stars, archives that preserve human culture, until the universe itself grows cold and dark. The universe has shown us that information storage on cosmic timescales isn't just possible, it's inevitable. The discovery of pristine ribose in space could transform biotechnology by providing insights into pure RNA-based biological systems. Before DNA evolved its double helix sophistication, life may have operated entirely on RNA chemistry that was simpler but more versatile than our current biological systems. Understanding these primordial systems could lead to new biotechnologies that are more adaptable, more robust, and capable of functioning in environments where DNA-based life would fail. We might develop biological systems that could thrive in space itself. Asteroids rich in organic molecules could be deliberately targeted at sterile planets to accelerate the development of prebiotic chemistry, rather than waiting for life to emerge naturally over millions of years. Future civilizations might seed worlds with chemical complexity by carefully orchestrating asteroid impacts that deliver sophisticated molecular toolkits to promising environments. This could transform barren worlds into biologically active ones in centuries, rather than eons, creating a new form of planetary engineering that works with cosmic processes rather than against them. If asteroids distribute complex molecules universally, there might exist patterns of molecular information that connect different regions of the galaxy. We might discover that chemical signatures from one stellar system appear in another, suggesting communication networks operating through molecular rather than electromagnetic means. The galaxy might be alive with chemical conversations that span light years and operate on timescales of millions of years. Civilizations might leave molecular messages that persist long after their radio signals fade into cosmic background noise. Terrestrial evolution might be influenced by continuous influx of extraterrestrial molecules, creating chemical selective pressures that we haven't yet recognized. Our planet's biological development could be shaped not just by internal processes, but by cosmic chemistry that arrives with every meteorite and dust particle. Life on Earth might be far more connected to galactic evolution than we ever imagined, receiving chemical updates from space that influence evolutionary pathways in ways we're only beginning to understand. The molecular preservation mechanisms discovered in BENNU might inspire treatments for aging and cellular degeneration. If cosmic processes can maintain molecular structures for billions of years, perhaps we can develop interventions that protect biological molecules from the damage that causes aging. We might learn to create cellular protective systems modeled on the organomineral complexes that preserved BENNU's chemistry, extending human lifespan by orders of magnitude. The universe might teach us how to preserve not just information, but life itself across extended timescales. Complex organic compounds from space could be processed into highly efficient biological fuels for space exploration. Rather than carrying massive fuel loads from Earth, Future spacecraft might harvest energy-rich molecules directly from asteroids and comets, creating sustainable exploration strategies that use the cosmos's own energy storage systems. Entire space economies could emerge based on harvesting and processing the chemical wealth that permeates the solar system. The specific molecular patterns found in BENNU could serve as templates for detecting prebiotic or biological activity on exoplanets. Instead of searching only for water and oxygen, we might look for the spectroscopic signatures of complex organic chemistry that indicates planets where molecular evolution is approaching the threshold of life. We could identify worlds where life is about to emerge centuries before biology actually appears. Watching chemical evolution progress toward consciousness in real time, humanity must expand its identity beyond that of a planetary species. We need to recognize ourselves as manifestations of galactic-scale chemical processes, participants in cosmic evolution rather than isolated accidents on a single world. This philosophical shift could fundamentally transform how we approach space exploration, environmental stewardship, and our responsibilities as conscious beings in an interconnected universe. We're not separate from the cosmos, we're the cosmos becoming aware of itself. Asteroids and comets require protection as universal chemical heritage sites. These objects preserve irreplaceable records of molecular evolution that belong not just to humanity, but to any conscious beings that might emerge anywhere in the universe. We need international protocols that preserve the most scientifically valuable small bodies for future study by civilizations we can't yet imagine. Some asteroids might be more precious than entire planets when measured by their chemical information content. The discoveries demand expanded global cooperation for systematic exploration and data sharing. No single nation can afford to study the millions of chemically interesting objects in our solar system alone. We need collaborative frameworks that pool resources and ensure that chemical discoveries benefit all of humanity rather than being restricted by national boundaries. The cosmos belongs to consciousness wherever it arises, not to the political entities that happen to explore it first. Science education must be revolutionized to incorporate this cosmic perspective. Children should learn chemistry and biology not as isolated Earth-based phenomena, but as local expressions of universal processes. Every chemistry experiment becomes a connection to cosmic evolution. Every biological observation, a window into galactic-scale development. Students should understand that when they study molecular interactions in the classroom, they're investigating the same processes that operate in asteroid laboratories billions of miles away. Young scientists will grow up understanding that their laboratory work connects directly to processes operating across unimaginable spatial and temporal scales. This perspective could inspire generations of researchers who see their work not as academic exercises, but as participation in cosmic evolution itself. The motivation to understand chemistry becomes motivation to understand the universe's own creative processes. Every scientific discovery becomes part of humanity's contribution to the cosmos's growing self-awareness. The legacy of this small 490-meter asteroid extends far beyond its physical dimensions. BENNU has transformed forever humanity's understanding of its place in the cosmos, proving that even apparently insignificant objects can carry secrets capable of redefining reality. In the vast library of cosmic knowledge, BENNU has turned out to be a volume that rewrites the entire catalogue, forcing us to reconsider everything we thought we knew about the universe's capacity for creativity and consciousness. As we continue to analyze these precious samples and plan future missions to other small worlds, we're not just conducting scientific research, We're reading the universe's own autobiography, written in molecular languages that predate the formation of planets. Each discovery brings us closer to understanding not just how life began, but how the cosmos itself has been evolving toward consciousness, complexity, and perhaps purposes we haven't yet begun to imagine. The universe isn't just stranger than we supposed, it's more creative, more alive, and more purposeful than we ever dared dream.